In this video, we're going to look at testing the overall model, or in other words, testing the significance of the overall model. So here, once again, the overall model is beta sub 0 plus beta sub 1, x sub 1, and so on. So this is the regression equation, which represents the mean of y, mu sub y given x, mean of y given x, plus a random error term. Now, if the regression is significant, then at least one of the slope coefficients, not the intercept, but if all the slope coefficients are 0, so that means this entire slope part will be 0 and it will only be a constant plus a random error. So that means the regression need not, we don't have to consider the regression. Regression is insignificant. It is not significant. As opposed to the alternative that not all of them are 0. Okay? At least one is different from 0. So null hypothesis, all slope coefficients equal to 0. Alternative is not all of them are 0. Okay? At least one is different from 0. Now, for us to be able to test this hypothesis, we have to make a certain set of assumptions. Now, right now we will only go over the assumptions, but later there are ways to validate those assumptions to see whether those assumptions are valid or not. And what if some of those assumptions are not valid, and what mitigation efforts can, or things that we can do to mitigate those assumptions that are violated. Okay. First assumption is the model itself, that is the expected value of y given x, that is the mean of y, okay, is that regression equation. Okay. Assumption 2 is the value of y is that the mean of x plus a random error. So here there are some typos. Okay. So actual value of y is the mean of x, y given x, mu sub y given x, plus an error term. So you have the expected value of y plus random error. Now, having defined the random error in this way, then the expected value of the random error is 0, and there is no bias in the regression analysis. So that is the assumption number 3. So usually first 3 assumptions will be stated as a single assumption, but your textbook separates them into 3 different assumptions, which is fine. Now the fourth assumption is these error terms, okay, are uncorrelated. And this is a very important assumption because in time series analysis, this is the assumption that may not be valid in most situations. So we have to do something to mitigate this particular aspect, because since these are time related, okay, what happened in one time period usually is going to have an impact in the next time period. So you cannot say the error in one time period is completely independent of the error in the previous time period. There will be some relationship. But for now, let's assume this assumption that the error terms are independent. We will look at what happens, how to test this and how to mitigate it later on in this chapter. Okay. Then next assumption is also about the error. The variance of the error is same all across the x values. For all the x values, okay, the amount of variance you see in the error term is going to be the same. Okay. That is another way of saying this is homoscedastic assumption. Once again, we will see what happens when this assumption is not true and how to mitigate it. And then the last assumption is the normal distribution assumption. The error values fluctuate in a kind of a normal distribution fashion. So once these 6 assumptions are verified, then we can do an F-test for the overall significance, and that F-test is MSR divided by MSC. We've already gone over the ANOVA table, and then you use the F.inv.rt is the F table value. We can do an F table value test, or F.dis.rt for a p-value test. Okay. So now let's go to the Excel file and do this test in Excel. Okay, so testing for overall model. Okay, and the hypothesis is stated in this fashion. All slope coefficients equal to 0, not all slope coefficients are 0. Then we have the assumptions. The first assumption, The expected value of y is given by this regression equation. The actual y value is the expected value of y given x plus the random error. The expected value of the random error is 0, that is, there is no bias. So the fourth assumption is the error values are independent of all predicted variables values. So fifth assumption is the variance of error term is the same for all values of the predicted variables. So finally the error terms, the E follows normal distribution. So given these assumptions, for our problem, the hypothesis must be stated in this way. Okay, so there are 4 slope coefficients. So all 4 slope coefficients equal to 0. Not all of them are equal to 0. Then we set up an alpha value. So let's assume alpha is 5%. Okay, so now we'll test using the Ftest with the F table value. So we've already computed F here, MSR over MSE, back up here in the ANOVA table. So that's our F table value, F calculated value. Okay, and then we have numerator degrees of freedom, which is that. And then we have denominator degrees of freedom, which is that. If you want to use the F table value, now for F table value, we have to use f.inv.2t, RT, sorry, f.inv.rt, okay, alpha value, comma, the 2 degrees of freedoms. So that will give us the F table value, and since the F calculated value is greater than the F table value, we reject the null hypothesis that all slope coefficients are equal to 0. So the conclusion is that. Now the p-value, okay, and we've already computed the p-value, but we will do it again. f.this.rt, the f value, comma, the 2 degrees of freedoms. Since this is e to the power of minus 100, so it's really a small value. Okay. So since p-value is less than alpha, we reject the null hypothesis. Okay. Now, so what is how do we interpret this conclusion? That is, we have sufficient evidence to conclude that the regression between the 4 predictor variables, okay, and the price of unleaded gasoline is significant. Not all the slope coefficients are equal to 0, and the type 1 error, the probability that this conclusion is in error, that is type 1 error, is nearly 0. So we have sufficient sample evidence to conclude that the regression between price of unleaded gasoline per gallon in a given month in the US as the dependent variable, the 4 variables, so price of crude per barrel, unemployment rate, S&P, and personal disposable income all lag by 1 month, is significant. The probability this conclusion is wrong is nearly 0.